Welcome back, physics studies. So let's talk about the charge to mass ratio that J.J. Thompson's was trying to find, this elusive property of this electron that he's, this particle. He didn't know it was an electron at this point. So every time I look away, the filter loses my face. It's kind of fun. So when the beam of electrons accelerates to a speed of this, okay, so directly perpendicular, travels in a circular path. Okay, so let's just, so this is down here is his velocity selector, right? So usually you would do the velocity selector part first, determine the speed of the electron that's coming out through the accelerated part, and then pass it through a magnetic field like this, and it creates a little circular path, and you measure the radius of curvature. So usually you would do this part down here first. Actually, I'm going to jump down here first, and then I'm going to go back to the other one because this is the order you would do it in. So these electrons would be accelerated to a speed, right? To a speed that we don't know, to lots of different speeds. So this is the first piece that happens. That's the first thing that happens. Maybe I should use a highlighter to do that. This is the first thing that happens here. Then the second thing that's going to happen is down here. These electrons, after the acceleration, are going all different speeds, and they pass through a velocity selector. And the beam electrons that pass through undeflected are the ones we care about. So let's go down here and actually try to determine the speed of electrons that pass through undeflected through a magnetic and electric field. Now, I'm not too concerned about the setup of the machine. Like, which way is the field going? Is it going up? Is the electric force going up? Is the electric force going down? Is the magnetic force going the other direction? All I know is that they are opposing each other. It causes undeflection. So all I care about for this question is that if I have an electric force, it must be balanced out by the magnetic force to remain, where is that? Undeflected. Undeflected is technically not a word. I should probably hyphenate that, but whatever. Okay, so it's undeflected. So I know these two forces have to balance each other out. Okay, so look at my formula sheet. The electric force in a parallel plate system is the electric field times the charge. I'm just doing the same thing we just did in the last video, the very last part of the last video. The magnetic force is caused by the speed of the particle and the charge of the particle and the magnetic field that's in. And we did this last class or last video where we just kind of canceled those ones out there. And we've rearranged for the speed. I'm kind of ignoring the absolute values that should be here. I'm not worried about direction. I just know that they're opposing each other. And then you just divide the electric field by the magnetic field. So we've got 50,000 newtons per coulomb. So it's 50 kilonewtons per coulomb. So I'm going to change that to regular newtons per coulomb, divided by 0.50 Teslas. Now, I'm not going to go through the unit analysis of this, but it does work out. It'll work out to meters per second as long as you change it from kilo to regular. So let me just get my calculator out here. 50,000. That's too many zeros. Divided by 0.5. Okay, so this is going at a speed of 1.0, only 2 sig times 10 to the power of 5? Yeah, power 5 meters per second. Okay, so now he knows how fast those electrons are going. All the other ones, if they go too fast, they slam to the bottom plate or the top plate. If they're going too slow, vice versa, they go the other way. Only the ones that are just going the perfect speed are going to go through undeflected. So now he knows how fast the particle beam is. You kind of split it a little bit, but he just knows the right speed here. So he takes that and he passes it through the next part of this. So this is the third part. Right here, yeah. This third part of his little device here. They use a different speed in this question. It's not going to be we're not going to use the 100,000 here. We're going to use the 593,000 here, but that's okay. We'll use that one. So this is now directed perpendicular to a uniform field. It travels in a circular path, determine the charge to mass ratio. So here's a nice little picture down here, what's happening. They give us a little hint of what to do. So what we know is that the magnetic field force, is the same as the centripetal force. They're just labeled the same. And we did this last time, m times a, which is going to be AC for this part. This is m times a as well, but we'll use the QVB part to do that one instead. Just substitute things that we know. Cross one of those velocities off there, and we're going to find charge to mass here. So I'm going to divide the B down to the other side. Cool. So this is where P got stuck before, but now because we have the velocity selected, we know the speed of these electrons, which is 593,000 meters per second. Yeah. You can just leave it in scientific notation. I just like doing that. You want to get away from microteslas here. So my magnetic field is going to be 100 microtesla. So micro times 10 to the negative 6, I believe. Teslas. Okay. And my radius, I want to put that in regular meters. So 3 point, oh, it's all the numbers are here, sorry. Times 10 to the negative 2 meters. I'm going to punch out my calculator really quickly here. So we get a number for the charge to mass ratio of this particle to be 1.76 times 10 to the 11 coulombs per kilogram. Okay. So you need to repeat this experiment. So J.J. Thompson would just do this experiment again, change the velocity selector a little bit, get a new velocity. You can leave the third part completely the same. Doesn't have to change that. You just measure a new circular radius, get the charge to mass ratio again. You keep on doing that. Keep getting these charge to mass ratios, and you'd always get the same charge to mass ratio. Then you'd change out the metal that's in the cathode over here. All right, maybe change that to gold, change it to silver, change it to aluminium, change it to copper, change it to whatever. Repeat the experiment again, and you'd always get the same charge to mass ratio. If you want to compare this to an electron's charge to mass ratio, because we kind of know what it is, it says here, a beam of electrons. But if I take the electron's charge and its mass, and just divide the two numbers, these are the accepted values. Mm-hmm. 1.6 e to the negative 19 divided by 1 e to the negative 31. Well, look at that. You get 1.776 as well. It rounds up, just slightly off by the thousandth decimal place there, but you get the same number. Okay. Just a little bit off. If you added more sig digs, it wouldn't be quite the same, but they're close. So they end up being the same, and every time we did the experiment, they always ended up being the same. This is the question I was talking about before. Would an alpha particle approaching from the opposite side through this undeflected machine here, would it also be undeflected? Yeah, probably, because the only thing that it depends on, yes. As long as it's going the other direction, because it's going the other direction, you use your right-hand rule, it'd be attracted to the opposite plates. It'd be forced the other way because of the magnetic field. But it would be undeflected since the speed is independent. Maybe I should spell independent properly. Ooh, independent of the charge of the particle. Okay. V is equal to E divided by B. There's no charge in there. It's only about the fields that it's traveling through. So it would have the same speed, but it would have a different charge to mass ratio when you go up here. If you have more mass, you would have a larger, because they're going the same speed, but you have a more mass, you'd have a larger radius, because more force would be required to push you off course. So you'd have to be a little bit farther. But you also have a bigger charge. Well, it gets a little bit trickier if you try that. Okay, it'll work out though. You'll be able to find the charge mass ratio, but it'll be a different charge mass ratio. What do we have on here? Oh, we haven't got to his model yet, so I have 5 minutes to get to his model. Okay, that's not bad. We can do that. Okay, so find the kinetic energy of the electron moving in an arc of 0.1 meters perpendicular to a magnetic field. Ooh, this guy, what were they asking here? So they want to know what the kinetic energy of an electron moving in an arc. Now, the key is that, okay, we know it's an electron, so we know it's charge in this question. So they give us that information. So that's good. So we know it's charge, we know it's mass. Dalton would now, all he would know is just the charge to mass ratio. So maybe we could just use his number, or just use the charge to mass ratio. Where did I put that number? Right here. This is 1.76 times 10 to the 11. So let's pretend that we are Dalton, or not Dalton, J.J. Thompson. So we know the charge to mass ratio. So I'm going to write that down. We know the magnetic field that this particle is in. We know the radius of curvature, according to this thing. Okay, so to find out the kinetic energy, we need to find the speed of this particle. Kinetic energy is just 1/2 mv squared. We're going to need the mass. So we are going to have to just take the fact that we do know the mass in this case, but we can find the speed without the mass just by using the charge to mass ratio here that we know. So let's find this, let's figure out what we have to do this. So we have the magnetic force caused by the charged particle inside the magnetic field. It's moving in a circle, so it's circular motion. So I'm just going through all these steps again. QVB. You can put the absolute values on that if you want. Cross those off. That's what we're looking for. We're looking for that speed. So I'm going to divide the mass down times the radius up, and we'll leave the B where it is. So that's what that looks like there. Now the Q and the M, that's my charge to mass ratio. You could put in numbers like the charge and the mass of the electron here, but we're not going to do that. I'm going to use the 1.76 number here. You get a more precise answer if you use the two actual numbers. I'm having fun with this charge to mass ratio though. Meters divided by B. That's supposed to be -4. Okay. So how fast is this electron traveling here? Well, I'm going to use the number here. It's not quite rounded, but I'm going to use the non-rounded answer we had from the question previously. Times it by 0.1 divided by this number. Sorry, that was my wife. No poop. I'm gonna have to. Oh, I had this upside down. Oops. Do I have this upside? I had this B here. That's why this thing was going so fast. Oh, surprised you guys didn't catch me on that. Well, you probably did. You're probably yelling at your computer screen saying, "Mr. Allen, you put this in the wrong spot." The B should be on the top, not the bottom. What was I thinking? What was I thinking? Let's times this by, oh, just 1 second. By this number, and I get a speed of, all right, so we get a speed of I'm going to write this out. This is going to be a tricky number. 1.76 times 10 to the 1, 2, 3, 10 to the 6 meters per second. There you go. Pretty good. Now, from there, we can use that to find the kinetic energy, because that would be the next part of the question. Because now I can go 1/2 mv squared, assuming that we know the mass of this particle, which let's say we did know the mass of this particle. It's just an electron, so we're going to use the 9.11 times 10 to the negative 31 times my speed squared times 1/2. So I get a kinetic energy of 1.41 times 10 to the negative 18 joules. Yeah, why not? Let's just change it into electron volts. So I'm going to divide it by that number, the 1.69 times 10 to the negative 19, and this is 8.81 electron volts of energy. I'd be okay if you just left in joules. Okay. Okay. Here we know. Yeah, so here we know carbon 12's ion. Carbon 12 is an isotope of carbon. We'll talk about the 12 stands for in a bit. If you've done some chemistry, you probably know already. This ion, so it doesn't have any electrons, has a charge to mass, it doesn't have any valence electrons, sorry, they probably got stripped out. Has a charge to mass ratio, blah. Calculate the radius of the ion's path. If it's traveling 150,000 meters per second in a 0.5 Tesla magnetic field. Okay, let's see what we have here. So we're inside a magnetic field, so we're experiencing that force. We're traveling in a circle because I have something in radius here. So that's my FC. So I'm just going to put my formulas that we know. And we're trying to find the radius. I'm just going to move this around. My R, I'm going to times the R up to this side. mv squared divided by qvb. Let's cancel out one of those velocities, make this formula a little bit nicer for us. Okay. So we have this charge the mass, the carbon 12 ion. The thing we do, the carbon 12 ion, I don't know what the charge of the ion is. It could be +2, +1. It could be negative because carbon could be positive or negative, right? I don't know its mass either in kilograms. I can look at the periodic table. It's not going to be very helpful because the numbers on the periodic table are an average of all the isotopes that you have, that you could have, right? So carbon 12 is a very specific isotope that has a very specific mass, which I don't know, okay? But I do know its charge to mass ratio. So its charge to mass ratio is 8.04 times 10 to the negative, or positive 6. Okay. I know the speed. I'm going to just write these down so I can scroll down afterwards. 150,000. I'm going to change the killian to regular meters per second there. I know the magnetic field strength. I don't know the direction of the field, but I do know it's just the magnitude of it. So I'm going to rearrange this formula just slightly because I have to figure out where does this Q over M fit in, because this is upside down. This is M over Q. So I'm going to move the M down to the bottom. So I'm going to do this instead. That mathematically is the same as the one above, because when you divide by a fraction, you're going to multiply by the reciprocal. The M is going to flip up to the top anyway. So I can move the M down to the bottom so it's with the Q over M like that, so it matches this over here. So now I can isolate, or not isolate, substitute my numbers. So 150,000 meters per second divided by the 8.04 times 10 to the 6 coulombs per kilogram and 0.5 Teslas. So now I can find this radius of curvature pretty good here. So 150,000 divided by 8.026 divided by 0.5. So I get a radius of curvature of 0.03 7. I think there's like 2 sigmas in this question, isn't there? Yeah, that ion, or the magnetic field strength limits our number here. So 3.7 centimeters. There we go. Okay, so the charge and mass ratio is a useful number if you don't know the properties such as the mass of the charge of the particle. And that's what he didn't know. He didn't know those two things. But he did conclude, because of all his experiments and seeing that all these charge and mass ratios were the same, he can conclude that these negatively charged particles are inside every single atom, and they're all the same, right? Maybe the other parts of the atom are not the same, but at least they have these negatively charged particles inside them that we can pull out. So that kind of breaks Dalton's billiard ball model. His model was that these atoms are indestructible. You can't pull pieces out of them. You can't break it apart. But J.J. Thompson was just spitting out electrons like crazy out of these atoms. So he had to make a new model called either the plum pudding model or the raisin muffin model. The plum pudding it's not like a pudding like we know. It's more like a bun, right? And there's little pieces of plum inside them. So this plum pudding model and this raisin or the raisin muffin model, right? Where these negatively charged particles, you can see here, these little blue things are the negatively charged particles, which we know are electrons now, are inside of this kind of fluid of positiveness. Here's a better picture, right? I have it labeled. Now, so at this point, he doesn't know about protons. He doesn't know about neutrons. He just knows that there's these negatively charged particles inside them that he can get out. But he doesn't know what makes up the rest of the atom. So the atom itself, to him, is just positive fluidness. Kind of just all spread out, no individual pieces. So you can see what he thought was, he thought this was incorrect on this side here with the little positive and the negatives kind of interspersed between them. He just thought as much a negative inside this positive fluid. Okay. So that's his model. We're going to talk about the next person, Rutherford, and how he disproved J.J. Thompson's discoveries here. Bye.